The spectrum of a time series describes how the variance of the data is distributed over the frequency components into which may be decomposed. This distribution of the variance may be described either by a measure or by a statistical cumulative distribution function, the power contributed by frequencies from 0 up to. Given a band of frequencies, the amount of variance contributed to by frequencies lying within the interval is given by. Then is called the spectral distribution function of. Provided as an absolutely continuous function, then there exists a spectral density function. In this case, the data or signal is said to possess an absolutely continuous spectrum. The spectral density at a frequency gives the rate of variance contributed by frequencies in the immediate neighborhood of to the variance of per unit frequency. The nature of the spectrum of a function gives useful information about the nature of, for example, whether it is periodic or not. The study of the power spectrum is a kind of generalization of Fourier analysis and applies to functions which do not possess Fourier transforms. An analogous definition applies to a stochastic process. Furthermore, time may be either continuous or discrete. Intuitively, the spectrum decomposes the content of a signal or of a stochastic process into the different frequencies present in that process, and helps identify periodicities. More specific terms which are used are the power spectrum, spectral density, power spectral density, or energy spectral density. The variance of has units which are the square of the units of. Therefore, these are also the units of or, and so the units of the spectral density are the square of the units of per unit frequency. In the case of the voltage of an electric signal, is proportional, except that it has the wrong units, to the power of the signal, and so even in statistical applications which use different units, the spectral distribution function and density function are often referred to as the power spectral distribution function and the power spectral density function, although the word power is often omitted for brevity in contexts where no misunderstanding will arise. The use of the power spectrum is most important in statistical signal processing and in the branch of statistics consisting of the analysis of time series. It is, however, useful in many other branches of physics and engineering, and may involve other units. Usually the data is a function of time, but they may be a function of spatial variables instead. Blackman and Tukey gave the classic definition in 1958, a Euro-cubed spectral density, a value of a function whose integral over any frequency interval represents the contribution to the variance from that frequency interval, a Euro-cubed. Explanation: in physics, the signal is usually a wave, such as an electromagnetic wave, random vibration, or an acoustic wave. The power spectral density of the signal, when multiplied by the appropriate factor, describes the power contributed to the wave, by a frequency, per unit frequency. Power spectral density is commonly expressed in watts per hertz. For voltage signals, it is customary to use units of V2HZA1 for the PSD and V2 as RHZA1 for the ESD. Often it is convenient to work with an amplitude spectral density, which is the square root of the PSD. The ASD of a voltage signal has units of VAHZA1/2. For random vibration analysis, units of G2HZA1 are frequently used for the PSD of acceleration. Here G denotes the g-force. Although it is not necessary to assign physical dimensions to the signal or its argument, in the following discussion the terms used will assume that the signal varies in time. Preliminary conventions on notations for time series. The phrase time series has been defined as a collection of observations made sequentially in time. But it is also used to refer to a stochastic process that functions as the underlying theoretical model for the process that generated the data. Furthermore, the time can be either continuous or discrete. There are, therefore, 4 different but closely related definitions and formulas for the power spectrum of a time series. If or is a stochastic process, we will refer to a possible time series of data coming from it as a sample or path or signal of the stochastic process. To avoid confusion, we will reserve the word process for a stochastic process, and use one of the words signal, or sample, to refer to a time series of data. However, the reader should be aware that in the engineering literature especially, This distinction is often conveyed instead by speaking of a deterministic signal but of a random signal for the process. Hence the value at a point in time of the deterministic signal is a number, denoted by, but the value at a point in time of a random signal is a random variable, denoted by the same symbol. Nevertheless, this article will preserve the distinction and use capital letters for the random variables and processes. For any random variable, standard notations of angle brackets or will be used for ensemble average, also known as statistical expectation, and for the theoretical variance. Motivating example, suppose, from 2 is a time series with zero mean. Suppose that it is a sum of a finite number of periodic components. The variance of is, for a zero mean function as above, given by. If these data were samples taken from an electrical signal, this would be its average power. Now, for simplicity, suppose the signal extends infinitely in time, so we pass to the limit as. If the average power is bounded, which is almost always the case in reality, then the following limit exists and is the variance of the data. Again, for simplicity, we will pass to continuous time, and assume that the signal extends infinitely in time in both directions. Then these two formulas become and. But the root mean square of either or is, so the variance of is and that of is. Hence, the contribution to the average power of coming from the component with frequency is. All these contributions add up to the average power of. Then the power is a function of frequency is, and its statistical cumulative distribution function will be. Is a step function, monotonically non-decreasing. Its jumps occur at the frequencies of the periodic components of, and the value of each jump is the power or variance of that component. The variance is the covariance of the data with itself. If we now consider the same data but with a lag of, we can take the covariance of with, and define this to be the autocorrelation function of the signal. When it exists, it is an even function of. If the average power is bounded, then exists everywhere, is finite, and is bounded by, which is the average power or variance of the data. It can be shown that can be decomposed into periodic components with the same periods as. This is in fact the spectral decomposition of over the different frequencies, and is related to the distribution of power of over the frequencies. The amplitude of a frequency component of is its contribution to the average power of the signal. The power spectrum of this example is not continuous, and therefore does not have a derivative, and therefore this signal does not have a power spectral density function. In general, the power spectrum will usually be the sum of two parts, a line spectrum such as in this example, which is not continuous and does not have a density function, and a residue, which is absolutely continuous and does have a density function. Definition: energy spectral density. Energy spectral density describes how the energy of a signal or a time series is distributed with frequency. Here, the term energy is used in the generalized sense of signal processing. That is, the energy of a signal is. The energy spectral density is most suitable for transients that is, pulse-like signals having a finite total energy. In this case, Parseval's theorem gives us an alternate expression for the energy of the signal in terms of its Fourier transform. Here is the frequency in hertz, that is, cycles per second. Often used is the angular frequency. Since the integral on the right-hand side is the energy of the signal, the integrand can be interpreted as a density function describing the energy per unit frequency contained in the signal at the frequency. In light of this, the energy spectral density of a signal is defined as a physical example of how one might measure the energy spectral density of a signal, suppose represents the potential of an electrical pulse propagating along a transmission line of impedance, and suppose the line is terminated with a matched resistor. By Ohm's law, the power delivered to the resistor at time is equal to, so the total energy is found by integrating with respect to time over the duration of the pulse. To find the value of the energy spectral density at frequency, one could insert between the transmission line and the resistor a bandpass filter which passes only a narrow range of frequencies near the frequency of interest and then measure the total energy dissipated across the resistor. The value of the energy spectral density at is then estimated to be In this example, since the power has units of V2 IV1, the energy has units of V2 as ZA IV1 and equals J, and hence the estimate of the energy spectral density has units of JA HZA1, as required. In many situations, it is common to forego the step of dividing by so that the energy spectral density instead has units of V2 as ZA HZA1. This definition generalizes in a straightforward manner to a discrete signal with an infinite number of values such as a signal sampled at discrete times. Whereas the discrete Fourier transform of the sampling interval is needed to keep the correct physical units and to ensure that we recover the continuous case in the limit. However, in the mathematical sciences, the interval is often set to 1. Power spectral density. The above definition of energy spectral density is most suitable for transients, that is, pulse-like signals, for which the Fourier transforms of the signals exist. For continued signals that describe, for example, stationary physical processes, it makes more sense to define a power spectral density, which describes how the power of a signal or time series is distributed over the different frequencies, as in the simple example given previously. Here, power can be the actual physical power, or more often, for convenience with abstract signals, can be defined as the squared value of the signal. For example, statisticians study the variance of a set of data, but because of the analogy with electrical signals, it is customary to refer to it as the power spectrum even when it is not, physically speaking, power. The total power P of a signal is the following time average. The power of a signal may be finite even if the energy is infinite. For example, a 10-volt power supply connected to a 1-key copyright resistor delivers 2/A equals 0.1 a W of power at any given time. However, if the supply is allowed to operate for an infinite amount of time, it will deliver an infinite amount of energy. In analyzing the frequency content of the signal, one might like to compute the ordinary Fourier transform. However, for many signals of interest this Fourier transform does not exist. Because of this, it is advantageous to work with a truncated Fourier transform, where the signal is integrated only over a finite interval, 0, a t. Then the power spectral density can be defined as. Here E denotes the expected value. Explicitly, we have. Using such formal reasoning, one may already guess that for a stationary random process, the power spectral density and the autocorrelation function of this signal should be a Fourier transform pair. Provided that is absolutely integrable, which is not always true, then the Wien-Rayuro-Kinchian theorem makes sense of this formula for any wide-sense stationary process under weaker hypotheses, does not need to be absolutely integrable, it only needs to exist. But the integral can no longer be interpreted as usual. The formula also makes sense if interpreted as involving distributions instead of functions. If as continuous, Bochner's theorem can be used to prove that its Fourier transform exists as a positive measure, whose distribution function is f. Many authors use this equality to actually define the power spectral density. The power of the signal in a given frequency band can be calculated by integrating over positive and negative frequencies. Whereas the integrated spectrum whose derivative is. More generally, similar techniques may be used to estimate a time-varying spectral density. The definition of the power spectral density generalizes in a straightforward manner to finite time series with, such as a signal sampled at discrete times for a total measurement period. In a real-world application, one would typically average this single measurement PSD over several repetitions of the measurement to obtain a more accurate estimate of the theoretical PSD of the physical process underlying the individual measurements. This computed PSD is sometimes called periodogram. One can prove that this periodogram converges to the true PSD when the averaging time interval t goes to infinity to approach the power spectral density. If two signals both possess power spectral densities, then a cross-spectral density can be calculated by using their cross-correlation function. Properties of the power spectral density. Some properties of a PSD include, the spectrum of a real-valued process is an even function of frequency. If the process is continuous and purely indeterministic, The autocovariance function can be reconstructed by using the inverse Fourier transform. It describes the distribution of the variance over frequency. In particular, it is a linear function of the autocovariance function in the sense that if is decomposed into two functions, then the integrated spectrum or power spectral distribution is defined as cross-spectral density, given two signals and, each of which possess power spectral densities, and it is possible to define a cross-spectral density given by the cross-spectral density is thus the Fourier transform of the cross-correlation function. Where is the cross-correlation of and? By an extension of the Wien-Rayuro-Kintian theorem, the Fourier transform of the cross-spectral density is the cross-covariance function. In light of this, the PSD is seen to be a special case of the CSD for discrete signals xn and in, the relationship between the cross-spectral density and the cross-covariance is estimation. The goal of spectral density estimation is to estimate the spectral density of a random signal from a sequence of time samples. Depending on what is known about the signal, estimation techniques can involve parametric or non-parametric approaches, and may be based on time domain or frequency domain analysis. For example, a common parametric technique involves fitting the observations to an autoregressive model. A common non-parametric technique is the periodogram. The spectral density is usually estimated using Fourier transform methods, but other techniques such as the maximum entropy method can also be used. Properties: the spectral density of and the autocorrelation of form a Fourier transform pair. One of the results of Fourier analysis is Parseval's theorem, which states that the area under the energy spectral density curve is equal to the area under the square of the magnitude of the signal, the total energy. The above theorem holds true in the discrete cases as well. A similar result holds for power. The area under the power spectral density curve is equal to the total signal power, which is the autocorrelation function at zero lag. This is also the variance of the data comprising the signal. Related concepts: most spectrum graphs really display only the power spectral density. Sometimes the complete frequency spectrum is graphed in two parts, amplitude versus frequency and phase versus frequency. The original function cannot be recovered from the amplitude spectral density part alone. Information about the phase is lost. See spectral phase and phase noise. The spectral centroid of a signal is the midpoint of its spectral density function, that is the frequency that divides the distribution into two equal parts. The spectral edge frequency of a signal is an extension of the previous concept to any proportion instead of two equal parts. The spectral density is a function of frequency, not a function of time. However, the spectral density of small windows of a longer signal may be calculated and plotted versus time associated with the window. Such a graph is called a spectrogram. This is the basis of a number of spectral analysis techniques such as the short-time Fourier transform and wavelets. In radiometry and colorimetry, the spectral power distribution of a light source is a measure of the power contributed by each frequency or color in a light source. The light spectrum is usually measured at points along the visible spectrum, in wavelength space instead of frequency space, which makes it not strictly a spectral density. Some spectrophotometers can measure increments as fine as 1 to 2 nanometers. The values are used to calculate other specifications and then plotted to show the spectral attributes of the source. This can be helpful in analyzing the color characteristics of a particular source. Applications: electrical engineering. The concept and use of the power spectrum of a signal is fundamental in electrical engineering, especially in electronic communication systems, including radio communications, radars, and related systems, plus passive, remote sensing technology. Much effort has been expended and millions of dollars spent on developing and producing electronic instruments called spectrum analyzers for aiding electrical engineers and technicians in observing and measuring the power spectra of signals. The cost of a spectrum analyzer varies depending on its frequency range, its bandwidth, and its accuracy. The higher the frequency range, the more difficult the components are to make, assemble, and test, and the more expensive the spectrum analyzer is. Also, the wider the bandwidth that a spectrum analyzer possesses, the more costly that it is, and the capability for more accurate measurements increases costs as well. The spectrum analyzer measures the magnitude of the short-time Fourier transform of an input signal. If the signal being analyzed can be considered a stationary process, the STFT is a good smoothed estimate of its power spectral density. These devices work in low frequencies and with small bandwidths. Coherence: see coherence for use of the cross-spectral density. See also, noise spectral density estimation, spectral efficiency, spectral power distribution, brightness temperature, colors of noise, spectral leakage, window function, frequency domain, frequency spectrum, bispectrum. Notes. References. External links: Power spectral density MATLAB scripts.